Okay, so for using the t-distribution, I'll show you how to do it with the critical value table and through technology too. But the t-distribution is something we use when we don't know the population standard deviation. If you did know it, then you could use the z-table, which is simpler. But in most cases, in real life, we don't know the true population standard deviation, so we have to use a t-test a lot. And so calculating your t-test value is the same way as those z-scores that we've done. What you'd want to do is take your sample mean, subtract it by the population mean, then divide by the sample standard deviation, S, and that needs to be divided by the square root of the sample size. So in this problem, the researchers, their mean systolic blood pressure for the researchers' sample group is 135, and the population value we're comparing it to is 141, and then the standard deviation is 5, and then we divide by the square root of 18. So this calculates our t-value. Okay, so I'm going to do the denominator first. Figure out what the square root of 18 is. I'm going to copy that to my clipboard. That way I can do 5 divided by the square root of 18. Copy that to my clipboard. Then the numerator, 135, subtracted by 141, divide by the denominator. So I got a t-value of negative 5.09. Did I do that right? Yep, that looks right. Negative 5.09. Okay, so we need that to help us out with the table, because the table will get you something called a critical value, which means if you're beyond this value, then you have something statistically significant. So we've got a negative 5.09. That's pretty big. It's probably going to be statistically significant, but let's complete it just to make sure. So you enter the table by using your degrees of freedom, and if it's a one sample test, then all you have to do is take your sample size, subtract it by 1. So 17 is our degrees of freedom. So that means the critical value we're going to compare our test statistic to is somewhere on this bottom row here. If degrees of freedom of 10, we'd use that row. Okay, what else? So we got the bottom row. Oh, and I didn't state what alpha is. Usually alpha is 0.05, and then it depends if you have a one-tailed or a two-tailed test for which row you're going to use. So I'm using alpha of 0.05, and my test is a one-tailed test because the question is the new medicine statistically significantly better? Which means our alternative, which is where we state, where we decide whether it's one or two-tailed. The alternative is that the new mean time is less than, 2 will be represent the new mean time. The new mean time is less than, sorry, not time. This new mean blood pressure is less than the old blood pressure. So the new medicine being better. So that's a one-tailed test. If it said, is the new medicine different, then that would be does not equals, and that's where you use the two-tailed test. So we're using a one-tailed test, and I said alpha is going to be 0.05. So we're going to follow this column down until we hit that bottom row that we said we need to use. So the positive test statistic, we just need to make it negative because t equals 0 is the center of the t-distribution. So if we have a left-tailed test, like a less than test that we just described up there, then we want a negative p-value. So negative 1.74 is our test statistic. And our value, sorry, I said that wrong. That's very bad. I hope I remember to edit the video. That is not our test statistic. That is our critical value. So negative 1.74 is our critical value from the table. We want to compare that to our test statistic, negative 5.09. So negative 5.09 is even further from 0. That means that yes, our new blood pressure medicine is statistically significantly better. It's doing something that's actually helping out. Okay. Because 135 is far enough away from the old 141, and based on the standard deviation of 5 and the sample size of 18, we can say it's not just by random chance. it really looks like the new medicine is doing a better job. It's statistically significantly better. Okay, and if you want to do that through technology, we use StatCrunch here. So you want to click Get More Help, StatCrunch. Let's see, I think, yeah, we want to go to Stat because that's where you see T-stats. And this is a one sample. We'd use two samples if we had two columns of data, and paired, you'd also have to have two columns. The difference between the two is paired data is like when you sample the same person twice to get each column. And we have a summary. We don't actually have the data set. You would click this one if you were able to copy and paste the data here, and then it could skip all the calculations for you. But we've summarized it because they've summarized by giving us the mean, by giving us the standard deviation, all that stuff. So the sample mean, that's what the researcher gathered for their own data. And we compare that to the population mean, which will go down here. We want to test and compare that to 141 for the population mean, because that's what mu stands for. Standard deviation is 5, sample size is 18. And then when you click compute, show critical value, we want to click that, and that's going to get the same critical value I just got from the table. Except this one says, oh, it's because look, it's a left-tailed test. I missed that option. So let's edit that. Look, that is a two-tailed test. It's supposed to be a less than test. So there's that critical value, roughly what we got from the table, negative 1.74, I think. Yep, that's what we got from our table. And then there's the test statistic that we calculated by hand. So if you have technology available to you, you can do all that stuff, so you can skip all the by hand calculations, and it gives you everything right here. But the big thing is the p-value. I mean, the p-value tells the same story. You don't have to do the test statistic and critical value stuff if you're able to successfully get a p-value. If the p-value is low, which means if the p-value is less than your stated alpha, less than 0.05 usually, then you reject the null hypothesis in favor of the alternative. It means you have statistically significant evidence that the medicine is better.